A quiz will be passed back during lab. SL in the syllabus, you have to put your course section on all your anything you turn in. Okay, a number of you did not, or you put the wrong course section. Please make sure you read the syllabus. If you missed out on the syllabus, you may have missed many other things. Okay? If you don't put your course section on, you're not going to get your papers returned. Okay? If it's not clear in the syllabus, let me know. The key has been posted. I didn't make a mistake on the video key. I corrected it on the hard copy key, and I made a note on the YouTube page. Just going a little bit too fast there. Any questions about the lecture material before we get going here? Any questions? Lots of real low quiz grades. 1s, 2s, and 3s. No questions about the material? No questions, it seems like you're highly confident. Question?
Yes, I actually have a question. This is actually from another worksheet, but it relates back to like the hybridization question. There's one hybridization of nitrogen that has three single bonds to it, and then there's another one with a double bond right next to it. How could you tell? Normally, how would you tell if the difference between a double bond that's like adjacent to where you would have to count the p orbital, and how would you?
Which question?
I would have to.
Which page are you looking at?
Oh, it was like the acid base worksheet.
Does it have a page number on it, or I'd like to be able to pull it up and look at it.
Oh, it doesn't have a page. It doesn't have a page.
That's not anything I did. I can look at that. Stop by now.
Okay.
Okay, guys, acid-base chemistry. Any questions thus far about what we've covered? Question?
I know this might be incredibly simple, but if you're comparing with resonance, the one that is more stable is the one that is like the weaker acid. Is that correct? Or is it reversed?
The one that is more stable, the one what?
That's like the structure in comparison to another.
I'm not clear on what you're comparing. Conjugate base?
Yes.
Okay. Conjugate base is an important term to be able to use. You're comparing conjugate bases. The one that's most stable, the original acid would be the most acidic.
Okay.
Is that what you said? Okay. I think we finished up with inductive effects. That was number 2. Okay, we're ready to look at resonance effects, which is number 3. Look at these two compounds. This alcohol versus this carboxylic acid. Which is more acidic? Well, we call that an acid, so hopefully that's more acidic. But why? Well, we need to look at the stability of the conjugate bases, right? And ask which is most stable. Okay, which is most stable? This is the conjugate base of that, that's the conjugate base of that. Which is most stable? We can look at inductive effects. This induction here is there, sp3 carbons. an sp3 carbonate inductively donating here. Here, though, this oxygen is withdrawing this way. And that's away from this oxygen, because any line away, no matter if it branches, is away. If it was coming this way, it would be towards, okay? It's just, the road just curved, but the road is going away from the oxygen. These electrons are being pulled because you got this dipole here, so that's going to help. That right there gives you the answer. That would tell you the one on the right is more stable because it has some withdrawing there, just to help stabilize it. But that's not the main reason. The main reason here is resonance or conjugation. Okay? Resonance and conjugation. I described some of that here. You need to start reading about that and figuring out what resonance and conjugation is. Be working problems. Okay? All right? Your textbook should have plenty of problems and discussion of resonance. Yeah? Okay? Take home from me here, I'll go ahead and get to it, is whenever this becomes a conjugate base, the oxygen takes on a new lone pair, right? 2 lone pairs here. Now it has 3. Same over here. Now it has 3. If that extra lone pair has something to do, if it has, and that's going to be some bonding, that's going to make it more stable. If it's just isolated and nothing to do, it's not going to be as stable. What's hybridization of this oxygen here on this compound? Hybridization. Why sp3?
Because it has that one bond with the carbon and the other lone pairs are in the p orbitals.
No, sp3 doesn't have a p orbital. Hybridization of this oxygen. It's sp2, correct? Yeah? Okay, everybody good with your hybridization? The main exception, anytime a lone pair is next to a p orbital, going to want to be in a p orbital. Okay, there's a p orbital next here. One of these lone pairs is in a p orbital. That's not oxygen, it's going to be sp2, trigonoplanar. Okay? One of the lone pairs is in a p orbital. It's got something to do. It's participating in some bonding interaction, which is a good thing. What about these lone pairs over here? What type of orbitals are they in? What's the hybridization of that oxygen over there? That one's just sp3. There's no p orbital next door. Plain old sp3. Okay? sp3, and of course sp3 doesn't have any p orbitals. This is sp2 with 1 LP in p orbital. And that's the stabilizing factor. That lone pair interacting with the neighboring p orbital leads to lots of stability, and it makes that anion more stable than the other anion. We say that this lone pair is delocalized, and we'll do more of that type of delocalization. This lone pair is not delocalized. All those lone pairs are just isolated on that oxygen. So there's sort of the take-home. P orbital has got something to do. One of these lone pairs is sort of participating in pi bonding with the neighboring carbon p orbital. You got to be able to see that. That's why this is so much more stable. That's why this guy is so much more willing to give up the H and become the anion. Okay, other things with resonance. We'll start drawing resonance structures. That is alternative structures for the same compound, just showing movement of the pi electrons. Whenever you do resonance structures, you never move atoms, only the pi electrons. The movement of the pi electrons can be directed by polarity considerations, and also just sort of learning how to move electrons. But in terms of polarity, this oxygen is more electronegative. It wants electrons. It's pulling. There's a dipole here. Pi electrons, though, are easily polarizable. That oxygen can pull that pi bond up towards it. Okay? And on the board, on our paper, we can just move these electrons up. And if you do that, you get to this structure. The electron is now up here. Lone pair is now up here. Single bond. Charge now. And since we only move pi electrons, that's a resonance structure. We can actually then keep on. This carbon now needs an octet. We can ask this oxygen to share these electrons. Okay, I'm using arrows. What does the arrow mean? WDAM. It moves, the pi bond moved up. It became a lone pair. It means, this is what it means. It gave us this. What does this arrow mean? Move these in. What does it mean? We now have a pi bond between the O and the carbon. That's a resonance structure. Okay? Then we'll talk about hybrids. The true structure of this compound here, this anion, is not this. It's actually a blend of all these resonance structures.
Dr. Stevens?
Whenever you have resonance, an individual structure you draw is not the true structure. Resonance is more of a blended type of structure. Okay? Question?
Yes, while we're looking at this structure, for the first one, could you show or tell us how many pi electrons, or if you had to count how many pi electrons are in the structure?
What's your answer?
I have no idea. My guess would be 2.
What's a pi electron?
An electron in a p orbital.
Okay, how many electrons in p orbitals? I see 4. I see the pi bond.
Okay, so 4 total electrons, 2 pairs.
Well, there's a bonding pair and a lone pair. If you want to call it 2 pairs. But usually when I hear pair, it's usually a lone pair. The bonding pair is a pair too.
Is it, so it's just those 2 in those bonds? What about the lone pairs on the oxygen?
Oh, well, what type of orbital are they in?
Mm,
Go back to the beginning discussion. What's the hybridization of that oxygen?
SP, SP. 2.
Okay. No, it's sp2. Can you graph it?
I could if I sat here and did it, yes. So then is the key to figuring out the pi electrons graphing it then, and then looking what's in the p orbital?
Well, I highly suggested the graphing. I showed you how to do graphing because it's very important. I think it's very useful. And the graphing will show you what type of orbital those lone pairs are in. And they're only pi electrons if they're in p orbitals. If they're in a hybrid orbital, not pi electrons. All right, so you got to know definition of pi electrons. Okay. For me to fully understand what you're asking, I like to see your attempt on paper, and we can go from there. Because we got the explanation through just talking is not always clear enough. Question?
When you say it's a blend of all of these, like the hybrids, does that mean like in reality, like the electrons are constantly moving between like these 2 structures?
Kind of, but they're not constantly moving.
Okay.
We'll talk more like about colors. Pink. How do you pink? If I combine red and white, that creates pink. Okay. Pretend like the wall is pink. The shirt is pink. Okay. Problem is, pink is hard to show. Pink is the blend. Instead, we draw red and white on the board and say, hey guys, the true color here is sort of a blend of these 2. Can you imagine the blend of red and white? What does it look like? Pink. But you don't say that pink is constantly moving. It doesn't go back between red and white. It's just pink. It's just the blend. But the pink is very hard to draw. The pink is the hybrid. We can draw it. It's going to have partial bonds. It's down here. We'll talk more about this. We've already did the take-home message. We've already explained how you can look at that and tell why the one on the right is more stable, because the lone pair has something to do. The something to do is resonance. We have to thus continue to grow our understanding of resonance. That's what this is trying to get at here. Here's your hybrid, okay, partial bonds. And the true structure, how many bonds do you have between this C and this top of it? 1.5. Okay, how do you know? Because you look at your hybrids. There's 2 bonds between here, there's only 1 here and 1 here. So is it 1 or 2? It's somewhere in between. The blend is somewhere in between. All right? You just start reading about resonance, and we'll hit this several times. And then by test 3, we'll actually cover resonance. But you don't want to cover it in one day because it'll be like this. You've got to start working on it. Reading, writing your questions down, getting them answered. All right, resonance is one of the top 3 tenets of organic chemistry. You will never get away from resonance. Organic 2, resonance will, well, in organic 2, there'll be some assumptions that you know what resonance is. Of course, that's why we're here in Organic 1, to learn about things like resonance. Okay. Please read. Let's look at this example down here. This compound, succinimide, has a pK of about 8 to 10. This alcohol, about 16. Does that make sense? What about electronegativity? Most acidic H here, CH or OH? OH, you'd rather have minus on oxygen. So let's consider this anion. Most acidic H here, CH or NH? NH, you'd rather have minus on nitrogen. But that's just internally. Now let's compare the 2. Which is more acidic? This NH or that OH? OH? Well, actually, no. If you know pKa, you see that it's less acidic. pK over here, it means more acidic, right? Why is this more acidic even though it's nitrogen? You'd rather have minus on oxygen, right? Yes, if that was all that was going on. There's more going on here. What's going on here with this guy? Look at this. 3 lone pairs here with the conjugate base. Is one of those lone pairs doing anything, or are those lone pairs just isolated? They're just isolated. They're just sp3. They're not doing any of this fancy pi bonding that we call resonance. What about one of these lone pairs? One of these lone pairs is in the p orbital. Why? Because there's p orbitals actually next to her on both sides. No, you only can put 1. Because you're just going to have, there's the neighboring p orbitals. You're just going to have 1 and it's going to overlap. Okay? Because if you put both, the other one would be like this. And it ain't overlapping with the neighbor. Okay? This is sp2 with 1 LP in p orbital. Same thing we said for above. All right, we're considering the anion. One of those lone pairs is doing something good. That's why this one's so much more acidic. Thus, it looks like resonance is a bigger factor than just electronegativity. It outweighed the oxygen. Not always. In this case it is. Resonance does tend to be more important than electronegativity. If there was only 1 carbonyl there, this would be more acidic.
That would still be a p orbital, right?
Yes, it would still be in a p
So it
orbital,
doesn't matter then.
but that would still be more acidic because the oxygen, minus on oxygen, is inherently better than minus on nitrogen. You will never, it's very hard for you to know the line where one thing matters and doesn't. In that example, resonance trumps electronegativity. In other cases, it may not. Number 4, hybridization effects. Hybridization effects. Look at the acidity of these compounds here. I indicated the H. All those are the same, so any of those. This H, SPCH, SP2CH, all those are SP3CH. This H is more acidic than this H, and this H is more acidic than any of those. What's the difference? Well, the conjugate base would be this anion here, like that, right? All these conjugate bases would be a carbanion, a carbon with an anion. So there's not a difference in electronegativity. So that's not it. Also, there's no resonance here, if you look at the conjugate bases. That lone pair is not in a p orbital, right? Okay? Well, hold on, or is it? Sometimes I make mistakes. That lone pair in a p orbital, what type? Okay? You got to know what type of orbital that lone pair is in. All right? One of the most important things of beginning organic chemistry. All right? The main thing here is hybridization effect. All right? This lone pair is in an sp orbital, where this lone pair is in sp3. And this one would be sp2, which is more stable. sp lone pair or sp3 lone pair? sp lone pair is more stable. Why? 50% S, 25% S. More S character makes it more stable. Why? Electrons closer to mama, closer to the nucleus. The negative electrons closer to the positive protons. Less separation of charge. The more you separate the charge, the higher the energy is going to be, and thus the less stable. All right? I'm sure you talk about charges in physics. Right? More stable. This is a hybridization effect. It's not an electronegativity effect or size of the atom or resonance. There's no resonance here. Very important effect. They're all important. Bases. What's the definition of a base? First off, what's the definition of an acid? Bronsted-Lowry acid. Okay. I don't particularly like that term. It doesn't, to me, saying donator is like if someone stole your bicycle, I would call you the donator of the bicycle. You didn't donate anything. Okay? I don't like the term. What's the definition of a base? Except the proton. I don't like that definition either.
Steve,
All right? That person stole my bike. Do you say he accepted your bicycle? He just accepted my bike. No, he took your bike. Okay? I would, if I taught Gen Chem, I would use those terms. I think it's going to help you more to understand what's going on, especially when you do error movement and do mechanism, which you should be doing. Okay? Bases take H's. All right? They don't accept them. They take them. All right? Acid-base reactions. Here we go. We got this carbanion. You put it in water. What's going to happen? I tend to circle lone pairs more and more. Good old acid-base mechanism, right? You've been doing your acid-base mechanism. You've been working on the warm-up question, et cetera, et cetera. These electrons, here we go. What do? They take the H. They don't accept it. Accept it is going to make you draw arrows this way, and then you're going to get it wrong. You're going to get a WDAM, and you're going to get like -5. You don't want that. You want to take the H. What happens here? These electrons move on to oxygen, the standard acid-base mechanism. What does that give? It gives this outcome. The carbon is now binding to the H. That used to be a lone pair. It's now binding to the H. And the oxygen has an extra lone pair. You also have charges. Okay? Of course, your base conjugate acid pair, one's charged, one's not. Other here, one's charged, one's not. Just like in Gen Chem. pKa's. All right, 1640, we need to talk about how to use your pKa's. Up there, the base was an anion. Okay, most good strong bases are anions. Okay, do not have to be though. Down here, ammonia is acting as the base, and these electrons may bond to H. These electrons move on to oxygen. Okay. Of course, anytime you do a reaction, you want to have a full structure. But you can't do a mechanism if you don't have a full structure. Sometimes you guys will do something like this, and it's like, there's no meaning here. This is insufficient. You need full structure. You need to show this bond being, okay, complete mechanism. This leads to this over here. Now this nitrogen is bonded to 4 H's, positive charge. I showed that condensed and we created hydroxide. It's all in your acid-base mechanism. Okay, considerations for bases are just the same as for acids, except it's reversed. Let's see what we mean here. Which is a stronger base? Ammonia or methylamine? What's the difference? Obviously the methyl. What does the methyl do electronically in a structure? What does the methyl do electronically in a structure? I can't hear you guys. Anybody over here? Right here, Atlanta Braves. What's your answer?
Does it do? Does it donate an electron?
Yeah. Would you say it louder for me like you're on the baseball field?
Donates an electron.
Donates a what?
Electron.
Okay. By what method or?
Well, the atom that wants it takes it.
What method or terminology we use for how this methyl donates electrons?
Induction.
Inductive? Inductive donation? Okay. There you go. We have inductive donation. Okay. Base. For this lone pair to go attack the H, why would it do that? Electrons are negative. And negatives like positives. Does that H over there have any positive character? Yes, it's bonded to the oxygen, which is greedy, so it has a dipole, leaving the H as partial positive. Okay? All reactivity is just pluses and minuses. Okay? Well, which is going to be partial positive? Let's call that constant. What if you had 2 different bases? Which one would be more attracted to the partial positive? The one with a little bit of electron density or a lot of electron density? A lot. The more negative, the more it's going to be attracted to the positive. Okay? So which lone pair is more negative? One on the right. Okay, because of the inductive donation by the sp3 carbon, the electron density at the lone pair side is increased. This is a stronger base. More, okay? Not all lone pairs are the same. Electron density. Okay? The electron density can be perturbed or changed due to electronic effects like induction or withdrawal. Okay? Which is number 2, which is more basic. Again, we're using the same 4 sort of electronic factors we did with acids, but we're sort of considering it a little bit differently. What's the difference here? They're both nitrogen, so there's no difference in electronegativity. The difference here is what? This lone pair is in an sp3. This lone pair is in what type of orbital? sp2. It's a hybridization effect. Which lone pair is going to be more reactive towards that positive H of an acid? sp3. Why? Yes, less S character, and thus what?
It's farther away from,
Farther away from the nucleus. Uh-huh. Here's a lone pair here versus here. You're a proton. Okay? You know, I could hear, if the lone pair's out here, it's like, here I come. Protons, where they at? Okay? All right? On the other hand, the other one's like this, held close to mama. Mama don't let the lone pair get out there and react with the protons. Hybridization effect. The electron is, the lone pair is not held as tight by the nitrogen, it's more out there able to react with protons. All right? Down here, this lone pair is in sp3. This lone pair is in what type of orbital? Yes, p orbital. And what do we know about lone pairs in p orbitals? They're busy doing resonance. They're busy conjugating. This lone pair is not interested in the H. It's busy conjugating with the p orbital right next door. It's got something to do. It's fairly stable. It's not interested in going to react with an H. Lone pairs in p orbitals typically not basic. Diminished basicity, diminished reactivity. They're preoccupied. They're doing something else. Yeah? More basic, be this guy. Yeah, more basic, be this guy. Number 4, which is more basic? But which is more stable? Cl minus, because it's larger. Since it's more stable, that hopefully means to you that it's fine being like it is. I'm very happy, stable. I'm just going to sit here on the beach with my Corona or whatever. I'm very stable. Okay? F minus not as stable. Which one of these wants to go back to neutral more then? F minus wants to go back to neutral more. It's not as stable. So it sees an H plus. I put this in quotations because this is not, doesn't actually exist. It's a partial plus. It's going to be more eager to get this and go back to neutral HF. That's a stronger base. Which is a stronger base, ammonia or water? What's the difference here? All these lone pairs are in sp3. They're in the same type of orbital. The difference is inherent electronegativity. Oxygen's more electronegative. It holds the lone pair tighter. It's a better parent. It doesn't let its lone pair get out there and react with protons. Okay? Nitrogen not as good a parent. It's not as electronegative, so the lone pair is not held quite as tight. It's more out there able to react. Ammonia is a stronger base.
Dr. Steven,
Uh-huh.
for number 2, if we were to talk about inductive effects, wouldn't the second one, would it have 2 arrows for inductive? The H going down and then the CH2 pointing towards the nitrogen?
No, you mean this?
Yes.
No. NH is, nitrogen is more electronegative than H.
Oh, yes.
That's why an NH will hydrogen bond, because the H is very partial positive due to the dipole. No, that's the wrong way. There may be other considerations. For number 2, the main thing there for me is a difference in hybridization. Which is a stronger base over here? They're both carbanions. They're both pretty basic. Both lone pairs are sp3. What's the difference? I got some extra inductive donation there. To me, that's the only difference, but that's enough. Which one's more basic? Correct? More electron density at the lone pair. So we used the same type of arguments we used before, except we understand that a base, the more available the lone pair is, the more electron density at the lone pair site, the stronger the base it will be. We have different ways to gauge that. Look at an acid-base reaction like back over here in the warm-up page. By the way, I need to send out answer keys to the warm-up pages. If I'm ever slow to do that, please remind me. I usually go by your questions. You start asking questions, I'm like, oh, let's get the warm-up key out. I mean, here's a reaction. What's the strongest acid on the board? HCl. It's one of the top 7 strong acids, right? There's your acid. Anytime you do an acid-base reaction, you're looking for the strongest acid and the strongest base. Those are the ones that are going to react. What's the strongest acid up there? HCl. So we got that. What's the strongest base up there? Hopefully it's in this molecule over here. But which atom is the strongest base? Because we need to focus in on atoms. And then do react. Where's the strongest basic site? That's the question. I'm not going to answer it right here. Okay? Please do that. Once you identify the acid and the base, then you do your acid-base mechanism and you show your products. Was there a question other than what's the answer?
I was saying just the alcohol.
No. But no, keep looking. This one good. Okay. Well, if we haven't said it already, which I think we did. Maybe this next page will help reinforce the fact. Neutral nitrogens. We said most good bases are anions. Hydroxide is your favorite base for most anything, right? Anion. All right? How many other bases do you know? You should know many others. Okay? Ammonia. Is ammonia anion? No, ammonia is neutral. Okay? Just about the only time a neutral atom is going to be a good base is nitrogens. See, oxygen holds the electrons tight, and a neutral oxygen, the lone pairs are just not reactive enough. It has to be an anion. But a neutral nitrogen, nitrogen's a bad parent. And a neutral nitrogen is often basic. Particularly then sp3. sp3 is your most basic. sp2 is still considered basic, but it's less basic. An sp lone pair on a nitrogen is getting pretty non-basic. And of course, a nitrogen lone pair that's in a p orbital would be considered non-basic. Neutral sp3 nitrogens and sp2 nitrogens are basic. Those are the types of bases that are found in nature, particularly organics. Now you can find carbonate in nature. Carbonate's a base. But that's an anion. In nature, your most common neutral bases are nitrogen-containing compounds. And a natural product that contains a neutral basic nitrogen is called an alkaloid. What does that term mean? What's a humanoid? Human-like? Okay. Well, alkaloid is alkaline-like. Alkaline meaning basic. Okay. They have basic-like properties. Called alkaloids, natural products with basic sp3, sp2 amines. Here are a number of alkaloids. A number of them are, very interesting structures. Getting to be a little bit complex with some rings. A lot of these have psychedelic properties. LSD is an alkaloid. It's called an ergot alkaloid because it's just the type of alkaloid it is. Okay. Which nitrogen of LSD is basic? Top, middle, or bottom? The middle one, yes. The other two are not, okay? Every one of these should have at least one. Anybody know any of these or seen these in biology classes? Or morphine, very important drug compound. First isolated from opium poppy in 1804. Who was the person who we can today call a chemist that did this and isolated this? And how did they isolate it? How did they know what they had and that it was pure? Have you ever heard of alkaloids in any biology classes or anything? Question?
Does that mean this like compound is morphine? Because it said it was found in the opium poppy. Does that mean it's also found in like poppy muffins?
Poppy seeds?
No, the chemical. Because it's originating from the poppy seeds, does that mean this compound can also be in the poppy muffins? Because the poppy muffins have like poppy.
I can't put poppy muffin.
Yeah, does that mean this compound is found in poppy muffins because?
It depends on what you make poppy muffins from. Talking about something you eat?
Yeah.
I mean, I don't know what it's made from. It's not, you know, the opium is mainly in the, I think, the flowering part of the, I don't know if it's in the seed. It's a latex. It's an oozing liquid that comes from the poppy, where most of these opioids are located. Is that the same part of the plant that's used to make poppy muffins? I don't know. You'd have to look into that. There may be a trace of some type of opiums in poppy seeds. Other ones, quinine. Okay, all these are natural products, meaning they came from nature. Nature produces them. Beautiful compounds, yeah? Okay, predicting equilibrium of acid-base reactions. Reaction will favor the side with the weakest acid. I think we showed this acid-base reaction before. This carbanion plus water is going to give methane plus hydroxide. You should readily be able to show that outcome. pKa's. Water 16, you should know that, just like alcohols. Hydrocarbon greater than 40, you should know that. Some of these are on the earlier table that we looked at. Which side has the weakest acid? Over here, 40 is weaker than 16. This side's favored. By how much? Difference in your pKa's, which is what? 10 to the 24? Right? Difference of 24? Log of 24, 10 to the 24 is your difference. The equilibrium lies to this side by how much? What's 10 to the 24? 100 gazillion, let's call it. Okay, that's a lot of zeros. All right, the equilibrium lies to this side. At equilibrium, you got 100 gazillion of these and only one of these. The equilibrium looks like this. I drew it like this to show equilibrium, but it really looks like this. Okay? I really need to draw that other way microscopic. This reaction is pretty much complete. It pretty much ain't in equilibrium. Okay? But all that answer is all should be there. You should understand this. And hopefully this also looks like all the math you did in like Gen Chem, right? Gen Chem 2, you do a lot of acid-base math. And you understand this from there. Let's look down here. If you take this compound, put it in water, we would expect to get this outcome plus this. pKa's, this is 5. pKa of hydronium ion is less than 0. Which side's favored? The side with the weaker acid, which is what? This side's favored. By how much? By at least 10 to the 5, depending on what greater than 0 really means. So, this equilibrium favors which side? This side. That is, if you put this compound in water, only a little bit will ionize. Majority of the compound will stay like this. This compound's acting as an acid here. If you want to say it's donating its H, you can say that. But remember, it's be careful with the terminology. It does have the acidic proton. It's acting as an acid, but it doesn't fully react. We call it a weak acid. It's acetic acid. It's a weak acid. It only partially ionizes in water. But understanding pKa's will allow us to predict that other than just memorizing something. Okay, down below, here's some for you to give products for and to determine which side is favored at equilibrium. There, and there, and there. Okay? And we'll look at those next time. All right? Predict products, tell which side is favored, and by how much. What about pH? How will an acid or base primarily exist at a certain pH? This is spelled out by the Henderson-Hasselbalch equation. You probably have not seen that. Nobody's ever seen that, yeah? You have seen that? Okay, then you know all this, yeah? Good to go? I'm actually surprised you have seen that. Usually that's seen in biochemistry, where you may derive the Henderson-Hasselbalch. Did y'all do any derivation of this? Or what did you use it for?
To solve the pH of the acids.
Do what?
To solve like from pH of the acids, you can look at pKa and the concentration of the base over acid.
Okay. Let's go through this. pH equals pKa plus log of the basic species over the acidic species. Okay? This is basically your conjugate acid-base pair. The ratio of them, log of B over A. Basically, there's a number of unknowns or variables here. If you know this and that, you can calculate pH. If you know pH and pKa, you can determine the ratio of B over A. And whatnot. The take-home from up there, if B is greater than A in terms of concentration, log of B over A will be positive if you just know math. Thus, pH will be greater than pKa. Because if you got pKa and that's a positive number, those are going to add up to a higher number for the pH, right? Okay? If the concentration of B is less than the concentration of A, the log of B over A is negative, thus the pH is going to be less than the pKa. In summary, there you go. If pH is greater than pKa, B will predominate. If pH is less than pKa, A will predominate. Make sure you understand the math and why. Acetic acid. How will it exist at pH of 7, which is blood pH? There's the question. How will acetic acid exist? What do we mean by exist? Will it exist in the acid form or the basic form? Any acid or base, you should be able to show both forms, the acid and the conjugate base, or whatnot. There's two forms depending on pH. Okay? We'll pick up here on Friday, including going back to the previous page. We'll finish this hand up on Friday, and we'll be moving into alkanes, cycloalkanes. I sent you that handout by email.